Welcome to Chapter 5, the final chapter of the Autonomous Driving Introduction series. In this concluding lecture, we'll tackle the biggest challenges that remain for autonomous driving, including edge cases, ethical dilemmas, and cybersecurity threats. We'll then explore vehicle-to-everything communication, examine how different countries are shaping their regulatory roadmaps through 2030, and look at the massive market forecasts that are attracting billions of dollars in investment. Let's begin by understanding why the last mile of autonomous driving is the hardest. One of the greatest challenges in autonomous driving is the long-tail problem. Common driving scenarios like highway cruising and standard city intersections make up the vast majority of miles driven, and current systems handle these well. But the remaining rare scenarios, the long tail, include extreme weather like blizzards and torrential rain, unexpected construction zones, approaching emergency vehicles with sirens, and unusual objects like a mattress fallen off a truck or a dog running across a highway. Each of these situations may occur once in thousands of hours of driving, yet the vehicle must handle everyone safely. This is why engineers often say that the last 1% of scenarios requires 99% of the engineering effort. Solving the long tail is what separates Level 4 from Level 2. The ethical discussion around autonomous driving has matured far beyond the famous trolley problem. In reality, autonomous vehicles are not making binary life-or-death choices between two groups of people. Instead, they engage in continuous risk minimization, constantly adjusting speed, lane position, and following distance to reduce overall danger. The German Ethics Commission published 20 guidelines that set an important precedent. These guidelines establish that human life must always be prioritized over property damage, that the system must not discriminate based on age, gender, or disability, and that manufacturers have a continuous obligation to reduce risk through software updates. On the liability side, different countries are taking different approaches. Broadly, Japan leans toward holding the Level 4 operator or service provider responsible. Germany's framework places more weight on the manufacturer while the system is driving, and the United States varies by state with no unified federal framework yet. All of these allocations are still being refined in legislation and case law. As vehicles become increasingly connected and software-defined, cybersecurity becomes critical. The main attack vectors include sensor spoofing, where adversaries trick LiDAR or cameras with fake signals to create ghost objects or hide real obstacles. CAN bus injection allows attackers who gain physical or remote access to send malicious commands to the vehicle's internal network. Over-the-air update hijacking could theoretically allow attackers to push compromised software to an entire fleet. And V2X manipulation could send false traffic information to alter driving behavior. To counter these threats, the industry employs a defense-in-depth strategy guided by standards like ISO SAE 21434 for cybersecurity engineering and the UN Regulation 155 for type approval. This layered approach includes hardware security modules, encrypted communications, network segmentation, intrusion detection systems, and secure boot processes, ensuring that no single point of failure can compromise the entire vehicle. Vehicle-to-everything, or V2X, communication extends the perception capability of autonomous vehicles far beyond their onboard sensors. V2X encompasses 4 types of communication. Vehicle-to-vehicle, or V2V, allows cars to share speed, position, and intent with nearby vehicles, enabling cooperative maneuvering. Vehicle-to-infrastructure, or V2I, connects vehicles to traffic lights, road signs, and toll systems for real-time traffic management. Vehicle-to-pedestrian, or V2P, alerts vulnerable road users through their smartphones. And vehicle-to-network, or V2N, connects to cloud services for map updates and fleet coordination. The technology debate centers on 2 competing standards: DSRC, based on Wi-Fi-like 802.11p technology, versus cellular V2X, or CV2X, which leverages existing cellular networks. The 5GAA Industry Alliance runs regular public demonstrations of CV2X, and automotive 5G modem vendors are adding satellite connectivity for coverage in areas without cellular infrastructure. Different regions are advancing autonomous driving regulations at varying speeds and with different approaches. Japan is leading with a Level 4 legal framework already in force, prioritizing highway freight and last-mile services across many regions. The United States is seeing state-by-state expansion of autonomous vehicle permits, while discussions about a unified federal framework continue. China has moved aggressively with full city Level 4 permits and a national target for Level 4 mass production. The European Union has amended its automated lane keeping system regulation to permit substantially higher motorway speeds and is developing a Level 4 type approval framework. South Korea has set its own national target for Level 4 deployment. The overall trend is clear. Every major automotive region is actively building regulatory frameworks, though the specific approaches reflect different priorities around safety validation, liability, and industrial policy. Autonomous vehicles are not just a technology story. They are reshaping the entire transportation ecosystem through mobility as a service, or MaaS. The vision is a seamless platform where users access robotaxis, public transit, e-scooters, and bike sharing through a single app, paying per trip rather than owning a vehicle. Robotaxi fleets are emerging as the backbone of this transformation. The Waymo and Uber partnership is particularly significant, combining Waymo's autonomous technology with Uber's massive rideshare platform and customer base. Beidou Apollo Go continues expanding across Chinese cities. The economics are compelling. Without driver labor costs, robotaxis can operate 24 hours a day at lower per-mile costs, potentially making ride-hailing cheaper than private car ownership in dense urban areas. Social acceptance remains a factor, however. High-profile incidents involving test and commercial fleets have repeatedly set back public trust and triggered permit suspensions, and a single serious event can slow an entire market. The market projections for autonomous driving are staggering. Market research firms put the global autonomous vehicle market somewhere in the hundreds of billions of dollars today, with 10-year projections running into the trillions. It is worth treating these numbers with caution. Different firms define the market differently, and their estimates for the same year can differ by an order of magnitude. What the forecasts agree on is direction rather than magnitude. Robotaxis are expected to take a growing single-digit share of ride-hailing, and autonomous trucking is widely expected to be the first segment to reach meaningful scale, because hub-to-hub highway freight is a far more constrained problem than urban driving. The key growth drivers include technology maturation, as AI models become more capable, regulatory progress enabling commercial deployment, declining hardware costs especially for sensors, and growing consumer acceptance as more people experience autonomous rides firsthand. Let's look at 5 key trends shaping autonomous driving in 2025 and 2026. First, end-to-end learning is accelerating, with Tesla, Waymo, and Huawei all moving toward unified neural networks that take sensor input and directly produce driving commands, replacing traditional modular pipelines. Second, foundation models and world models are emerging, with systems like Wave's Gaia series, Drive Dreamer, and NVIDIA Cosmos learning to simulate and predict how the driving world behaves. Third, simulation technology is advancing rapidly, with digital twins and synthetic data generation enabling testing of billions of miles of edge cases without real-world risk. Fourth, global regulatory frameworks are progressing simultaneously across Japan, the EU, China, the US, and South Korea, creating a more favorable environment for deployment. Fifth, significant challenges remain, including the long tail of edge cases, unresolved liability questions, and the need to build and maintain social trust. These 5 trends are converging toward a future of safe, scalable autonomous mobility. This concludes our 5-chapter Autonomous Driving Introduction series. Let's recap the journey we've taken. In Chapter 1, we covered the fundamentals including SAE automation levels, sensor technologies, and perception algorithms. Chapter 2 explored planning and control, from path planning to behavioral decision-making. Chapter 3 dived into the AI and software architectures powering modern autonomous systems, including end-to-end learning. Chapter 4 examined testing methodologies, simulation, and safety validation frameworks. And in this final chapter, we address the remaining challenges, V2X communication, global regulations, and the massive market opportunity ahead. The autonomous driving industry is at an inflection point, transitioning from experimental technology to a transformative global industry projected to reach trillions of dollars within the next decade. The convergence of advanced AI, supportive regulations, and proven deployment experience means that the future of autonomous mobility is not a question of if, but when and how. Thank you for joining this series.